we'll try and get out of here in a reasonable amount of time. So to do that, however, I'm going to have to do some derivations and stating of laws and things like that without any real depth to the derivation behind it. So a lot of times I'll state a law and the conditions under which it's true and when you can use it, but as far as proving it or giving you an indication or a little bit more detail on why it might be true, that I'll sort of point you in the right direction, but I can't do that. So, last time we got all the way up to centripetal force and centripetal research. I cut it off there rather than go into energy. So what we're going to start off with is energy, and then we're going to move into momentum, and then we're going to start doing, we'll do a little bit of Newtonian gravity, and then we'll do angular momentum and work. Okay, so there aren't that many broad topics to go over, but the topics are the more difficult. Let me remind you, and for those of you who were not here yesterday, of the sort of the framework that I'm going to try and cast all these problems in. The first thing I'm interested in doing is comprehending the problem or understanding it. That can also be identifying it. I think that some questions are worded in such a way that it's not saying, solve for the value of whatever or find a condition. It's sort of a more generally stated problem. And so understanding what you're being asked is the first obviously important part, but a lot of times that's missing. The second is understand the system. And this will really come into play, not so much last time, because last time we did a lot of introductory stuff where there wasn't a lot of depth in the physics there. There were some projectile problems, I suppose. But with energy and momentum and angular momentum, those are the really deep things in physics. And so from that point of view, understanding how the system works and what laws apply to it and how and what things govern the behavior of the thing will be a little bit more subtle this time. So that will be part B, and it's another important point that is oftentimes sort of taken for granted. The next part is identify a path to the solution, which sort of sounds like I'm just saying, well, let's solve the problem. But really what I mean is, before you solve the problem, can you see how the laws that govern the behavior of the system can connect what you already know, or what you're given in the statement of the problem, to a conclusion that you're asked to draw, right? So what if I wiggle over here is gonna change something over here? Where is the solution gonna come out of? What do I have to work? And lastly, part D, which is in principle the easiest part, is just grind out the algebra that's required. Okay. But this is the part that all of you are easily capable of doing once the problem's been set up. So again, the physics is in A, B, and C, while part D is just. So I'm going to put this in a box over here, and so every time we do an example problem, I'm going to try, when it's appropriate, to sort of pass the route to the solution in that. So the first thing, energy. So without doing any derivation, we remember that this is sort of the holy grail, right? Where F is equal to ma, which is mx double dot. Let me also state for the people that weren't here, I'm going to try and avoid as much as I can overloading variables, which is to say, if I can use x double dot instead of a, I'm going to do it. If I can use like theta dot instead of omega, I'm going to do it, because a lot of times much of the confusion is sort of coming out of the fact that we use the same or very similar variables for completely different things, or the same things in different contexts, and it can get kind of messy. So to avoid that, I'm going to do as much as I can to eliminate any overloading of variables and try and be as concise as possible. So I'll use double dot instead of a when I can. Now, what we also found, though, for those of you that were in my class and we actually did this derivation, this turns out to also equal via some sneaky calculus, this. Okay. And so what that means is, if I define this thing, and I'm going to call it capital K. In my class, I like to call it T, but just in the interest of stuff, I'm going to call it K with some serifs on it or something like that. And I call this thing the kinetic energy. And so apparently, the force on an object, F, is equal to the derivative with respect to the position of this kinetic energy. Another way to write that is if I integrate between 2 points, x1 and x2, the force, this is equal to the total change in kinetic energy.
Watch out.
Lots of buttons on the walls. So this is sort of the integral statement that corresponds to this. This is a very basic sort of calculus equivalence, fundamental theorem of calculus, whatever you want to call it. But if you integrate the total force, this is the net force now. This is when you add every force that's acting on the thing up. When you integrate the net force over some interval, then that's equal to the change in the kinetic energy over that interval. Okay? So from over here to over here, there's some forces acting on the thing, and I integrate from here to here. The force, the net force, what I'll get is the kinetic energy at the end minus the kinetic energy at the beginning. This is called the work energy theorem. And so we define this quantity, work, and we say, all right, work is equal to the integral of F dx. Okay? I'm going to put a little subscript I here. And the reason I'm going to put a little subscript I there is because for a particular force, you can calculate the work done by that force, right? So this is a very general statement. I can say the work done by this force is equal to blank, right? Or the work done by these three forces is blank, by just including that kind of thing, okay? So the work done by any force or collection of them is equal to the integral of the force or the collection of forces over whatever interval you like. Okay, so work is done over an interval, and the force is done, or the force is applied over that interval. That's what you're integrating. It's important to recognize that work is not a local quantity. Which is to say, I can't ask you, what is the work at x equals 3? That doesn't make sense. I can ask you, how much work has been done between x equals 0 and x equals 3? That's fine. But I can't ask you, what is the work at x equals 3? That doesn't make any sense. Okay. All right. So the three major things that you would write is, that you might write, are the net work, which is equal to the integral of the net force over whatever interval you like, points, is equal to the change in the kinetic energy. That's what we just wrote. Right? This is called, you normally call this is what you write as the work energy theory. I could also write the work done by a conservative force, which is going to be W-C-O-N-S, conservative, over that interval, x1 to x2. Can we just not lean against that wall? Yeah, there we go. Sorry, I apologize. There we go. Okay, so this is equal to the force applied by that conservative force. And this is equal to minus the change in the corresponding potential energy. Okay, the minus sign is extremely important. And lastly, the work done by the non-conservative force is equal to, and the same thing, and this is equal to change in the total energy, which is the energy, the kinetic energy plus the potential. So these are the big three. It's very important that when you're using one, or when you're thinking of one, or when it's sort of playing a role in your thought process or your solution, you understand what you're talking about, which work, right? There isn't just one work. And which quantity here it corresponds to. One more time, the net force, or the net work, which is the integral of the net force, is equal to the change in kinetic energy. The work done by a conservative force is equal to minus the change in the corresponding potential energy. And the work done by the non-conservative forces is equal to the change in the total energy. Okay? And you can see that if you add the work done by the non-conservative forces plus the work done by the conservative forces, you'll get the work done by the net forces. Right? So that makes a little bit of sense. Recalling, of course, that our definition E, this is our total energy, is equal to kinetic energy plus potential energy. If we have multiple forces acting, we might have multiple potential energies. So for example, I might consider a gravitational force and a corresponding gravitational potential energy, and I might consider an elastic force and the corresponding elastic potential energy, right? Or a Newtonian gravitational force and the corresponding Newtonian gravitation. Yeah.
Can you give us like a real life example and where we'd see each of these?
Or these?
Yeah, like what
Sure.
would be a purpose for using it?
For
And all three of them.
all three of them. Okay. So an example might be if you have an object, right, and it's moving from place to place. So here's x equals, x1, here's x2 or something. So you have an object that is just sort of moving around. And at the beginning and at the end of the trajectory, it's not moving. So for instance, start the timer. Go. And stop. So across that interval, I've moved the marker from here to here. Right? There have been forces applied to it. I've applied a force to it. Gravity is applying a force to it. The table's applying a normal force to it. There are all kinds of forces acting on the thing. But it's not moving at the beginning, and it's not moving at the end, so the change in the kinetic energy is equal to 0. What that means is there is no net work done. So whatever forces are acting on this thing, there's no net work being done on the thing if the change in kinetic energy between this point and that point is equal to 0. Okay? So that would be sort of an example. And when we get to the example problems, that'll be a little bit more concrete and not much, right? But this will be enormously important, right? Because the whole idea of this conservation of energy theorem, or conservation of energy law, or whatever you want to call it, right, relies on the assumption that there are no non-conservative forces acting. In general, the change in energy, which is the change in total energy, which is the energy at the end minus the energy at the beginning, is equal to the work done by non-conservative forces. It's not 0. They're not the same in general. But if there are no non-conservative forces acting in the problem, or if the work done by the non-conservative forces exactly cancels out, okay, then the energy is conserved. And only in that case can I say, E initial equals E final. So I'll do an example problem where E initial is not equal to E final, and we'll have to use this thing to make up the difference.
More on conservative and non-conservative.
So conservative force,
Non-conservative, right?
yes. A conservative force in general is any force that I can write in this way. So if I have a force, I'll call it F, right? It is conservative if I can write it like this. If I can write it as the derivative of something, then it's conservative. It seems pretty general, right? But you can't write friction as the derivative of anything. Nor can you write a force that I apply as the derivative of anything, right? Because I might push and then push a little harder and then push back. And there's no analytic function that would give you that kind of thing. So this seems like a weird condition, but it's related to the derivation of the conservation of energy in general. And basically all that tells you is if a force can be written that way, then it's conservative. It has a corresponding potential energy, which is U. And when you add all the U's together, with the kinetic energy, then that's your total energy, and it's conserved as long as the only forces acting are these. But if you have a non-conservative force, which we'll see in a second, that's not true. Okay. So, again, this is really the highlight, this last one, because it gives you the conditions under which the conservation of energy is true. If there are no non-conservative forces, or if the work done by the non-conservative forces cancels out, which it would be rare, but that would be like if friction were acting against something and I was pushing exactly to cancel friction out or something like that. In those cases, delta E is equal to 0, and I can set E final equal to E initial. But so let's see a couple examples of conservation of energy. So, this is a very simple one. Imagine I have an incline, angle is theta. I have a box that's sitting on the top of the incline, and this height is going to be 10 meters. This angle, I'll be concrete with it, is going to be 60 degrees. All right. Use this. Okay. So, the mass of the thing, we'll say m equals 10 kilograms. And as usual, for those of you who are not in my section, who weren't here last time, every time whenever I'm working, and the acceleration of gravity g, the acceleration due to gravity g, is equal to 10 meters per second squared. The functional difference between this and 9.8, and it makes me able to multiply it. Okay? All right, so this is frictionless. So my question is, I started here, I let it go, it slides down. How fast is it moving at the bottom? Right? This is the simplest, most basic example of the conservation of energy. So, what do we do? Well, it's frictionless. The only force acting on this is gravity, except for the normal force, right? Because the normal force is acting on this too. But we recall, right, that the normal force can never do work on anything. So, in terms of work and energy conservation, we can neglect all the normal forces. And so the only relevant force that's acting on this guy is gravity. And it's pulling down. And so it doesn't really matter what the force is, though, because I'm not going to break it up into components. I'm going to use the energy. So I'm going to say, all right, delta E is equal to 0, because there are no non-conservative forces acting, which means that E initial is equal to E final. E initial is the kinetic energy at the beginning plus the potential energy. I'll put U sub little g is the gravitational potential energy here. This is equal to, and then this is equal to K final plus. Right. And we recall that K, kinetic energy, is equal to 1/2 mv squared, and U sub little g is equal to mgh, where h is some height. Right? So again, it's important to recognize that at the beginning, I need to set a reference level. I need to set some place I'm calling height h equals 0. It doesn't matter where I set it, but there are some clever choices or some choices better than others. And so right now, the obvious choice is height is equal to 0 at the bottom of the incline. So the kinetic energy at the beginning is equal to 0, because it's not moving. There is no v when I just let it go. So this is 0 plus mass is 10 times g is 10 times the height is 10. That's 1,000. And this is equal to the kinetic energy at the end, which I don't know, because I don't know this final v. So it's 1/2 times 10 times v squared plus 0, because at the bottom the height is equal to 0. So I get this, solving that out a little bit, cancel 10. And so v squared 200. And so V is roughly equal to 14 meters per second. .1 or something. 14.1. Square root of 2. All right. Anyway, so I've solved the problem. V final. I should write this as V final. V final is about equal to 14 meters per second. That's fair. Okay. So that's the simplest possible example of something where this could be useful. Again, notice though that because I am using the fact that there are no non-conservative forces in order to start here. Right? So really what I'm saying is that should be first. It seems like I'm being kind of pedantic, but it's really important that when you have these problem-solving techniques that you're going in the right order of assumptions or the right order of steps. Because you can really quickly get kind of out of sorts when you don't start from the very basic assumptions. The very base thing that I'm saying is no non-conservative forces. So this, which implies this, this. I plug in my numbers and I.
So, like, say in the final we have a problem like this, and they just want like the final. Do we have to show like all those assumptions, or since?
I mean, no. So, generally speaking, like as a grader, if you write down the correct answer and there's nothing there, then I'm not going to assume that you cheated. Right? But if you write down the wrong answer and there's nothing there, I can't give you any points. So the more you write down, the better. This is probably getting excessive in terms of things that you need to write, right? Because you could probably start with this, and most graders would be like, okay, yes, energy is conserved. But for your logical process, first step should be, are there non-conservative forces? No. Then what? Okay, so that's a very simple example. Let's do a slightly more complicated example where now we can still use the whole energy idea, but now we have to take into account the non-conservative forces. And so it's exactly the same. Every parameter is exactly the same, except there is now a coefficient of kinetic friction between this block and this incline, and that mu k is equal to 0.1. So now what? First, are there non-conservative forces acting? Yes. So right off the bat, I cannot write that delta E equals 0, or that E initial equals E final. And what I really have is that delta E is equal to E final minus the E initial, which is equal to the work done by that non-conservative force, which is, in this case, friction. So I can still use this whole conservation of energy idea. E final is E initial plus this extra little contribution. Okay. So if the work done by the non-conservative forces is positive, which would be the case if, for example, I were following behind the block and shoving it down the ramp, then the final energy will be greater than the initial energy. If it's negative, then the final energy will be less. And that's what we're going to find. So we can do the E final, E initial, all that stuff is fine, but we should really find this first, because this is the big, stick in the spokes of the wheel of the bicycle. So the work done by the non-conservative force is equal to the integral of the work, of the non-conservative force itself over this length. But the non-conservative force, thankfully, is at least constant. So this is equal to the length here. So if I call this guy the length of the face of the incline, if I like, it's equal to the length times mu k times the normal force, denoted by n hat. Because that is what the force is, except I need to add something, and that little something I need to add is a minus sign. Because the force is acting in the opposite direction to the displacement. So I'm moving down the ramp, but the force is going up the ramp, and so I need to introduce a minus sign. Okay? comes from a point that I did not elaborate earlier, but in more than one dimension, when you have a possibility of moving one way or the other way, force under such a work is this. So you have this dot product until you get like a cosine theta. And so if the force is acting in the opposite direction to the displacement, you get a minus sign. If it's acting perpendicular to the displacement, you get 0, which is why normal forces can't really work. But that's an aside. So we're back to here. So the work is in fact negative. Right? And so what is it? Well, the length of the incline is really equal to 10 divided by sine of 60 degrees. Because 10 times the sine of 60 degrees is equal to length, so divide. No, length times sine of 60 degrees, sorry. And so this is the length, which I'll calculate in a second, minus sine, times 0.1, which is mu k, times the normal force. Oh, geez, what's the normal force? Well, if you recall, right, with a lack of other things pushing on the guy, if it's just gravity, then the normal force that comes out here is equal to mg cosine. And so that gives me a 10 m, right? And then a g gives me another 10 times cosine of 60 degrees. Ugh. Let's put it on the calculator in a second. And this happens to be equal to minus this 100 cosine 60 cosine 60, 150 cosine 60, 50.86. You're a man. Thank you. 50. Apparently equal to 57.7 minus 7. Yeah. Yeah, I know. I just divided by 0.86. Okay. Anyway, so this is the work done by the non-conservative force, apparently minus 57.7 joules. So now that I've calculated the work done by the non-conservative force, and it happens to be this, I can now use the conservation of energy. So I can say, all right, the energy, I'll just plug this in and not explain it again because I already did it. The final energy is equal to 1/2 mv final squared. The initial energy is equal to mg h naught, or h initial is 10 meters. Right? And I'm going to have minus 57.7. And so this is 5 the final squared equals mgh1 minus 57.7 and minus 942.3. This is 942.3 divided by 5. And square root.
You're in it. It's 13.70.
Okay. 13. Point what?
72.
Cool. All right. So that's how we would take into account a non-conservative force and still use the conservation of energy. And you'll notice that, of course, the velocity at the bottom is less than it would have been if there was no friction. 0.1 is a very low coefficient of friction. So this is a little tiny bit. And so the velocity decreased by a little. But if this were larger, you'd have a smaller velocity. Okay? Now, I should point out that it's also totally acceptable to calculate the net force on the thing, which is mg sine theta minus this frictional force, which is mu. Okay, that's the normal force. That's the net force on the thing. You can then divide that by the mass and get the acceleration. And then you use this as your length and go about your one-dimensional kinematics and your one-dimensional motion under a constant acceleration, and you would again find the final velocity equal to 13 meters per second. Meters. Okay, so there are multiple approaches, right? Whatever flavor you like. If you like conservation of energy, you can use it, even if they're not conservative forces, but you have to do this. You like 1D kinematics, it's a little bit harder to use, especially if the thing doesn't have like a constant slope or something like that. But you can use it if you like. Both will always work. Some just might be a little bit easier than others, depending on the point. So, do you have any questions about how we use the conservation of energy both with and without presence of non-conservative forces? All right, so that's the conservation of energy. We're going to come back to it in a little bit, where I do. I'm going to do conservation of momentum right now, and then what it's going to lead to is, you know, the ballistic pendulum problem where it had both. I'm going to have a slight variant of the ballistic pendulum where we're going to need to use both of those things, and then I'll really start illustrating how I'm thinking about it in terms of these 4 steps. So, conservation of momentum. You can also write this holy grail equation, F equals ma, rather than the derivative with respect to position of the kinetic energy. This can also be simply written as T of m, right? Or you prefer dt of mv. But I caution you that it's very important that you recognize that v is, number 1, a function of time, and number 2 is intimately connected to x. Right? That's sort of, and I mentioned this yesterday, but again, because there are a few people here today that weren't here yesterday, it's really important that you not abstract v away from x. They're not the same, obviously, but they're very intimately related, and in real-life physics, which is what you're going to get to after you hit this, one of your essentially main goal is to understand how to calculate what this is by integrating and differentiating with that. So the connection between x is extremely important, and you shouldn't think about it like it's just another number. Okay, so given this, this is not particularly enlightening or important for a single particle, but for more than one, I can say this. So if I have a system, right, so I have 1, 2, 3, be very careful, right, because this is teaching in college. You can't draw collisions between balls because you'll never really have. No, I swear it happens. That's what I did the first time, and it was like 45 minutes before people stopped giggling. It's very sad. So, I'll assume you guys are slightly older than that. So, we have, in general, this collection of objects. There can be 1, 2, 3, 5, 10, whatever you want. And each one of them has a particular mass, so this I'll call M1, M2, M3. And they may have some velocities, which is V1, might be going this way, V2, maybe this one, V3. Okay? Which means that each one of them has a momentum, which you define to be P, right? I say P I, so that's the momentum of the ith one. I equal to 1 or 2 or 3, is equal to the mass of the ith particle times the velocity of the ith particle. Notice I'm using vector notation because what's going to become important shortly is an understanding of how this is true component by component. So you won't always be able to find everything with one equation. You're going to have to play them off each other, very similar to when you did projectile motions. You had to play the x equation off the y equation and vice versa. So this is the momentum of the ith particle. So your system, your collection is made up of 10, 20, 30 particles. Each one of them has a particular momentum. If I define P total as equal to the sum over all the particles of their momentum, which is kind of weird to do because, you know, they're not related to one another, so the fact that I'm just adding them, I can do it because they have the same units and because they're both vectors. But the momentum of this one doesn't necessarily have anything to do with any of the other momentum. But if I add them all together, I get this thing called P total. As it turns out, this is equal to, well, if I do this, then the force, the sum of all the forces, is equal to the rate of change, d by dt, that is P total. So this is all the forces acting on each and every part. But what I find through some clever stuff involving Newton's third law is that what this really is the sum of all external forces. So the force that gravity exerts on these objects is an external force, for example. But the force that this one exerts on this one when they collide is not external. That's what I would define as internal. So internal forces are those between constituents of your system. And as it turns out, they all cancel each other out, which is a consequence of Newton's third law. Which means that the sum of all the forces on the system, if you add every single one up on a microscopic level, you really get the sum of all the external ones. If this happens to be 0, equals question mark. If this happens to equal 0, which it doesn't have to, but if it does happen to equal 0, then the total momentum of the system is constant. It's conserved. So the momentum of each particle might change, but the fact that, maybe they bounce off each other and they each acquire a new momentum, but when you add them all together, that total is always going to be constant if there are no external forces acting on the system. Notice that it doesn't have to be like a sort of a hard sphere like click, click like this, right? It could be, imagine that I put a little bit of C4 on the edge of this particular one and hit another and explode. Right? Those forces would still be between the individual constituents, which would mean that they're still internal, which would mean that they still cancel out. So the conservation of momentum is actually very general. If there are no external forces, then the momentum will be conserved, period. It doesn't matter how these guys are interacting with each other, but if the only relevant thing is how they bounce off, or how they connect, or how they do whatever, then momentum is going to be conserved. So that is the statement of the conservation of momentum. So let's see an example. Again, we'll do a simple example, and then we'll do a slightly more complicated one. So the simplest example is, now I use boxes. So this has a mass of, let's see, 2 kilograms. It is moving at 5 meters per second. And this one has a mass of 3 kilograms, and it's not moving. And they collide. So then what happens? Right off the bat, I cannot tell you. I don't know. Right? There's not enough information here for me to tell you what happens to these guys after. I can tell you that the total momentum is going to be conserved, that it's going to be 10 kilogram meters per second, distributed between one or the other. So I need to give you more. And so what I'll say is, let's just imagine that they hit and then they stay connected. So this is 2, this is 3, and then it's moving at some final velocity that I don't know. That is an input. You weren't able to figure this out beforehand, but I've given you this information that they stick together. So they're attached by Velcro, or they're soft, or they're clay, or they're sticky, or whatever. In some way, they stick together. So if they do that, then what's the final velocity? And that's easy, because I can say that the initial momentum, P initial, which is the total momentum, is equal to 2 times 5 plus 0, right? Because this isn't moving. And that's equal to 10 kilogram meters per second. And the final momentum is equal to 5, which is the total mass. Well, really, okay, I should, strictly speaking, they're moving together, so I'll say 2 times V final plus 3 times V final. But of course, you can just treat them as one lump. So this is equal to 5 times V final. And I can't say anything else. But because there are no external forces acting on this thing, right, I should have said earlier that this surface is frictionless and flat. Right? There are no external forces, there's no friction, there's no gravity, whatever. So this is conserved, this quantity called total momentum. And so we find that these things are equal to one another, and therefore that the final velocity is simply equal to 2 meters. Okay. That's about as simple as you could possibly make a conservation momentum. So now we'll make it slightly more complicated. Right? So, that V final is equal to 2, right? 2 meters. So what's the kinetic energy of this system? The kinetic energy here is 1/2 times 2 times 5 squared, which is equal to 25 joules. This is the kinetic energy before they deflect. What's the kinetic energy here? 1/2 times 5 times 2 squared, which is equal to 10. And so these are equal to one another. This is K initial. This is K final. And there is absolutely no reason that they should be. I have not said anything about what forces are acting between these guys, except that they're acting between the two. And so they could be conservative forces, or they could be non-conservative forces. And if they're non-conservative forces, there's no reason that they should be the same. And in fact, they won't be. So the energy might be lost, in this case, or it might be gained. So again, kind of joking about sticking a glob of C4 on the one, but if there was some kind of interaction that introduced new energy, a simple example would be chemical energy, right? So if there was an explosion of some kind, where energy that was previously chemical in nature becomes kinetic, then you're going to find that the final kinetic energy is greater than the initial kinetic energy. Also fine, because the conservation of momentum says nothing whatsoever about the nature of the forces acting between them, only that they are acting between the two. So the conservation of momentum is actually more fundamental than the conservation of energy in that sense. Because the conservation of energy says, okay, energy is conserved if all the forces are conservative. But this says momentum is conserved if all the forces are just acting pairwise, which is much simpler. Okay, so let me switch this up and we'll say, all right. So they undergo some kind of interaction. I don't know what it is, but I do know that at the end, the 3 kilogram block is moving this way at 2 meters per second, all by itself. No, not by itself. Let me say, make it 5 meters. So I have no idea what this guy's doing. So I'll just give it a name. We'll label it B final. Could be the other way, but if it's the other way, I'll just get a minus sign. So now what do I get? Notice that I have to give you something. I have to say that this one is moving at 5 meters per second. Otherwise, there's no way for you to figure it out, because it could be divvied up in any combination. So I have to specify one from which you can find the unknown. And so, again, the P initial, which is the momentum at the beginning, is equal to 10 kilogram meters per second. That hasn't changed. Okay. The final momentum, P final, is equal to 3 times 5 is 15 kilogram meters per second. Minus, plus 2 times V final, which I don't know. And again, because I claim that this is frictionless and flat, so there are no external forces acting, because of that, I can say that these will be equal to one another, and therefore that 10 is equal to 15 plus 2V final. And what that tells me is that V final is equal to minus 2.5 meters per second, which means that it's moving this way at 2.5. Also fine, in accordance with the conservation of momentum, but it's important to recognize that I need to give you more information. It's possible that I'm a jerk And the information I give you is the change in kinetic energy, which is also enough to figure out what it would be. But then you have to solve two simultaneous equations, one of which is quadratic, and it's kind of gross in the algebra is discussed. So not do that. And the easier way to do it, which is what you'll see if you see anything, should be specifying one of the final forms. In that case, it's pretty simple just to figure out what the other one is. Okay? So, momentum conservation, questions for me about that? Let's, real quick, just to be curious, I can tell you right now it's going to increase, but what is the kinetic energy change, right? So again, the initial kinetic energy is the same as before, 1/2 times 2 times 5 squared, which is 0.5 joules. And this is initial. And the final kinetic energy is equal to, well, I have this one, that's 1/2 times 2 times 2.5 squared plus minus 2.5 squared, but the sign goes away, plus 1/2 times 3 times 5 squared, which is going to give me, this cancels 6.25 plus 1/2 times 3 times 75, 438. No, 37. Right? 75. 75, 68, 73, yes. Right, and so this would give me a total of 3743.75. And so indeed, kinetic energy has increased, which again, I reiterate, is totally fine. There's no reason why it shouldn't, because I have absolutely no idea what is going on between these guys. Okay? Okay, so now that we've got that taken care of, let me just real quick do one other one. I'm going to set it up, and I'm going to ask you guys to do it yourselves because it's just time. But it's important to see how these things work as vectors. So I'm going to imagine that I have this. We have two that are, this one has some velocity. So we'll say this. This one is 2 kilograms, and this one is also 2 kilograms. This one is initially moving with speed 20 meters per second. Okay, and it collides with this. After the collision, we're now moving different angles. The angles are not necessarily the same. This is again 2 kilograms. 2. And so what I'm going to give you is we get 5 meters per second at now. No. 5 meters per second at 30 degrees. Okay? And what I want to know is two things. Number one, how fast is this one going? And number two, at what angle? So I'll let this one be V final that I don't know, and theta that I don't know. How on earth am I going to solve that? I treat it like a vector problem, right? So vectors are simply shorthand for a list of scalars. So if you have a vector equation, it's just saying it's true for the first component, and the second one, and the third one, and the fourth one, fifth, sixth. It's a list. So what this really means is that P initial x is equal to P final x. Again, by the way, I'm assuming the momentum conservation holds here, so there's no friction, there's no gravity. So P final x. And also in the y. So I'll set it up, and then you guys can give it a shot by yourselves if you're already, unless you're already familiar with it, in which case you can completely disregard whatever I'm going to say. Okay, so in the x direction, the initial momentum is 40. So 40 in appropriate units is equal to the final momentum in the x direction, which is 2. times 5 times cosine 30 degrees plus 2 times v final, which I don't know, times cosine of theta. Simultaneously, I have the y equation as well. In the y direction, there is no initial momentum because it's moving straight horizontally. And so I get that 0 is equal to, what's the final momentum in the y direction? This is 2 times 5 times sine of degrees minus, because the other one is moving down, minus 2 times v final times sine of theta, which I don't know. Okay. So look, magic trick, right? We found two equations. There are two unknowns. They're not easy to solve necessarily. Right? Sine theta and cosine theta are not easy, or it's not immediately obvious one from the other, but it can be done. So your goal now is to say, all right, here's this. And of this and out of this, there are two equations, two unknowns. I need to do some elimination or whatever I need to do. But can I calculate theta and can I calculate v final? And the answer to both those questions would be yes. So give it a shot. So that's momentum conservation and then momentum conservation in a vector point of view. But remember that when you're working with vectors, be it forces or momentum or whatever you're talking about, it's just a list. It's just saying that it's true for this component and this one and this one. So if you see a vector equation, you don't really know where to go, write it out in component form, like this equation, and this equation, and this equation, and see if that is helpful. All right, so now let's do that weird little example problem. That's, I said, it's a variant of the ballistic pendulum, and we're going to do this. Hey guys, I wanted to redo the problem that I gave in the second part of their final exam review because I realized, when I was walking out of the room, essentially, that I had just invented it in my head and I hadn't really thought it through. And so the answers that we got may not have made sense. So I went home and actually checked what the answers were, and there was, immediately a red flag. So what I'm going to do quickly is just show you what I did, and then why it was wrong, and then what the actual correct answer would be. Right? So if you recall, the setup for the problem was we had a surface like a ceiling, and then we had a spring that was connected to a mass, right? And call this mass M, and we had at the bottom a bullet that was fired from a gun, traveling upward at speed v naught, and it had mass m sub b for bullet. Okay, I'll make this guy a capital M. All right, so if you recall, what we did was we said, all right, we need to use the conservation of momentum first to determine the initial velocity of the bullet and the block together once they've stuck. Right? And then from then on out, we can use conservation of energy. So in principle, it was right, but I made a mistake. Okay, so I'll show you what that was. I'll use the actual values that we use just to be safe here. So I said this was 10 kilograms. Spring constant here was K equals 5 newtons per meter. This was 1 gram, this bullet, and it was moving when it hit the block at 1,000 meters per second. Okay, so the first part was we used the conservation of momentum to find the velocity of the block bullet system. We said that P initial was equal to just the mass times the velocity of the bullet. It's the only thing that's moving at the beginning, which turns out to be 1 kilogram meter per second. Okay. From there, we said, all right, so P final is, since they stick together, 10.001 kilograms times the velocity at the end, which I don't know. And we said that, because this is really, really small in comparison to 10, that the final velocity was, in essence, equal to 0.1 meter per second. Right? So, we got to that point, and that was right. So now we said, okay, well, we need to use the conservation of energy. So part 2 is the conservation of energy. So I say the initial energy is all kinetic. So that's 1/2 times the mass of the whole thing, which I'm just going to let be 10, times the velocity squared, which is 0.1 squared. And what I get from that is 0.05 joules. Okay. The final energy, this is E initial, right? E final is equal to, it goes up and then comes down and then sort of stops for a second, so there's no kinetic energy. It's all spring potential, right? So I said, if later on it ends up looking kind of like this, then what I'm looking for is this height h, this distance h. So I said the final is the gravitational potential at that point, which is minus m, which is 10 times g, which is 10 times h, which is unknown. Right? And then we also have the spring potential, plus 1/2 times 5 times h squared. Okay? And what this all led to was the quadratic equation 2.5 h squared minus 100h minus 0.05 equals 0. And then we were going to solve this and find out what the two values for h were. We said there's probably going to be one above and one below. Right. So we were almost right. The thing that I didn't take into account, of course, which was silly and a rookie mistake, right, was that I didn't take into account the initial spring potential energy, because it's really not what we would call a relaxed spring, because there's a mass attached to it. So when you attach a mass to a spring and hang it vertically, it stretches by some amount to compensate for the extra gravitational force. And so it oscillates about the new equilibrium point. Right? What you can often do is just treat it as though it's a regular spring, just shifted so it has a new equilibrium point and it's just regular harmonic motion again, which is fine. But if you're taking into account the amount of energy stored in the spring, then the amount of energy stored in the spring at the beginning is not 0. Right? It's 1/2 k times the initial stretch squared. So what I really should have written was this. For part 2, E initial is equal to that initial kinetic energy, which is 0.05 joules, plus the initial stretch distance of the spring. So, or the initial potential energy from that stretching of the spring. So the first question is, how far from equilibrium has it been pulled? And the way we do that is we say, all right, well, the force that's pulling up on the spring, which is k x naught, must be equal to the force that's pulling down on the spring, which is mg. Which means that x naught, the initial stretch distance of the spring, is equal to mg over k, which is 100, right? 10 times 10 divided by 5 equals 20 meters. I should really probably have used a more realistically tight spring. Like 5 is very, very small. As you can see, it's 20 meters hanging, but we'll bear with it for a moment. So what I should have said, right, is that the initial energy is equal to this plus 100, which is mg, well, 10, which is m, times g, which is, no, I'm sorry, my fault, plus 1/2
times 5 times 20 squared, which is 400, which is equal to 200 times 5, which is equal to 1,000. So it's 1,000.05 joules. Right? So the initial energy was way larger than this. So the initial kinetic energy plays a very small role. Okay, so what we'll have at the end is E final is equal to, again, the kinetic energy at the bottom will be 0, so we'll have minus 10 times G, which is 10 times the H, which is unknown, right? So again, this will be true. But then the final potential energy for the spring will be 1/2 times 5 times not H squared, but 20 plus H squared. Okay? So this again will give us a quadratic equation in H. But now it's going to be a bit more complicated. And so what we'll get, and this part right here, 20 plus H squared is H squared plus 400 plus 40H. So all told, the final quadratic equation I have to solve is 2.5 H squared plus 20 times 5, 100 minus 100. So I'll have, from this guy I get 40 times 5, which is 200, divided by 2, which is 100. So 100H minus 100H, and so I get no H term. And then the constant term is plus, this is going to be 400 times, or divided by 2, which is 200, times 5, which is 1,000. 1,000. I'm going to have to subtract the initial energy minus 1,000.05. So you see this 0.05 is not negligible. We can't let it go yet because it turns out to be the only meaningful thing. And this is equal to 2.5 H squared minus 0.05, and this must be equal to 0, which leads us immediately to the fact that H is going to be plus or minus the square root of, where am I, 0.05 over 2.5. Which will be 0.141, give or take, plus or minus 0.141 meters. So this will be our final answer. Okay? So, for those of you who come to the third review session, I'll go over this in a little bit more detail, but I just wanted to point out that I made a mistake with this part, and it would have been immediately apparent had we solved the quadratic equation that the distances were much too large. There was one that was very small and then another that was very large. It didn't make any sense. So there was a mistake made, and the mistake made, which was my fault, is that I did not take into account the initial potential energy stored in the spring because I was just very used to thinking of it in terms of oscillating about just a new equilibrium point. But when I do take it into account, I get this, and the answer comes out to be 0.141 meters. Okay? So that is that's the actual solution to that problem. It's quite involved. So instead, what I would suggest is if you wanted to practice a problem before the exam, you do something that is almost identical, but without all those additional gravitational complications. And so the problem that I would suggest as a revised version, if you wanted to practice, was if you had something that was just horizontal. Attached to a spring, here's a block, and you fired a bullet into it this way. Right? So what I would suggest is the following. Let's bring this mass down to 1 kilogram. Let's make the spring constant K is equal to 20 newtons per meter. Okay, let's make this bullet weigh, again, 1 gram and be moving at a speed, V naught is 1,000 meters per second. And now, it strikes the block, it'll compress a little bit, it'll stretch back, and the question is, how far will it stretch or compress? Okay, so after it's hit, it will look something like this. Okay, and so the question is, what will this distance be? Okay, which you might call delta x or whatever you like. Okay? So it again incorporates the same principles, except now the gravitational stuff has been kind of discarded because it causes a lot of additional complications. And what you're left with is simply this. Okay? All right, so there you go. That's a revised problem for you to practice, and the actual solution to the problem that that I introduced but solved incorrectly for you. Okay? See you guys. So, what is the difference between normal gravity and Newtonian gravity? Well, the answer is normal gravity, this minus mg thing, came after Newtonian gravity. His insight, so what I'll do, instead of explaining why this is more fundamental, I'll show you this and show you how constantly it comes out. So, Newtonian gravity, law that Isaac Newton discovered. That's it. So if I have two objects, call them 1 and 2, 1, this guy's 2, they're separated by a distance, which I'm now calling R12. I only give it a subscript to avoid overloading it, to try and make it clear that it's distinct from the other R's that we use a little bit. Then 1 exerts a force on 2, and 2 exerts a force on 1. They're attractive, which is the minus sign. And the value of the force, the magnitude, is equal to this. It's important to notice that this R12 is the distance between their centers of mass, not the distance between their edges, but the difference between their centers of mass. So in this system, maybe this distance and this distance are not all that important, but when you deal with planets, it's immensely important, and it's where I would probably estimate that the largest number of people who really know what's going on miss their points because they forget center to center, not edge to edge. Okay. So that's the idea behind the formula. That's where it comes from. And so, the first question, is this conservative? Can I write this as the derivatives or something else? Of course it is. And what function is this the derivative of? Maybe antiderivative. It's not, by the way. So it's really what I'm asking is f so g is equal to minus d by dr, in this case, or r12, u g. R is the spatial variable of interest. So the question is, what function u of g will give me this when I take the derivative and then give it a minus sign? And the answer to that question is still a minus g m1 m2 over r12. That's it. So this is the potential energy that corresponds to the force, and it's really important because they're exactly
exactly identical in every way except the force over r squared, potential energy over r. It still happens to be the same. Alrighty, so what cool stuff can we do? Well, first you should notice, right, that these objects now, the force is not constant. It's like the spring force, right, where when you moved between 2 points, the force that the spring exerts on you is changing. It depends on where you happen to be at that moment. The same is true of the gravitational forces. So all I'm going to do with the gravitational forces is I'm going to say, all right, let me say two things. Number one, I'm going to calculate the escape velocity of planet Earth. That's going to be one problem we're going to do. And the other problem we're going to do with this is to, the other problem is like the energies of a particular order. So those are the two problems that I want to do for Newtonian gravity. All right. First, also notice that this is negative always. Right? Because R12 is defined to be positive. It's the distance between them. And so this is like a well. Okay? It's sometimes referred to as a gravity well. Because if you were to graph the potential energy, U versus R12, it looks like this. Universally negative. Not that it particularly matters. It's only universally negative, by the way, if I say that, if I set the 0 point, right? So you remember in gravitational potential energy with the mgh bit, we have to say where h equals 0, which is where is the potential energy equal to 0. We have to do the same for this, and the normal definition, which is the only one anyone ever uses, is that the potential energy between two things is 0 when they're infinitely far apart. So if r is infinitely large and massive, this thing goes to 0. And so that's where we set the potential energy. Once we've done that, now it's universally negative. So, first problem, escape velocity. So here's the question. Here's planet Earth. Here's me. And I would like to jump really, really high to the point that I never come back. I escape completely. So how fast do I have to jump? How high? Or how fast do I have to shoot a projectile out or whatever? Like shoot a little golf ball out of it. I did my undergrad work in Alabama, and I had a Thanksgiving dinner with a family from northern Alabama. That was very, very, very sweetest family I ever met, but super backwoodsy. And I had weak students that would play piano, music stuff, and the others went out in the backyard and just shot things. Well, one of them invented a golf ball cannon, and he came in and he was like, "Hey, physics boy, how high does this thing go?" I was tasked with finding out how high the thing went. Fun fact. Anyway, so I'm shooting something up, basically the point. And my question is, how fast do I have to fire it so that it never comes back? Here's how I start. I say, what does it mean that it never comes back? No. Not R0, right? R would be infinite. R would go to infinity, right? So, but to be out there and then also moving, it means my potential energy is 0, but my kinetic energy is large, or not large maybe, but greater than 0, right? Not because it can't be negative, it's 1/2 mv squared. So my requirement is that I'm moving around a little bit, or I may be completely at rest, in which case it would be 0. But my potential energy is equal to 0. And what that means is my total energy is positive or 0. Right? So my condition that I've escaped E final has to be greater than or equal to 0. That's it. That's my escape condition. Where that E is the sum of my kinetic energy plus my potential energy, where the potential energy is universally negative. So, that's my escape condition, but I know that the only force acting on me as I'm flying away from the planet is gravity itself trying to pull me back. And it's conservative because it has an associated potential energy. So what that means is the energy at the end is equal to the energy at the beginning. So really my escape condition means that my initial energy is equal to 0. I'm sorry, it's greater than or equal to 0. And that's it. This is how I'm going to find my escape velocity. So I say, all right, my initial energy, the initial is equal to 1/2 m. I'm going to say m1 is me. Okay, little m is me. And capital M is the mass of the plane. mv squared. Okay. And then I have to add the potential energy minus big G, big M, little m, over what? Right. Is it 0? Am I starting from r equals 0? No. Where am I starting from? R is the radius of the Earth, so I have to say, all right, so this is the radius of the Earth, capital R. There's where I start. Okay? It's important that it's not from the edge, it's from the center. And so this must then be greater than or equal to 0, which means that if I divide by my little m and multiply by 2, I find that v squared has to be greater than or equal to 2g big M over r. And so v has to be greater than or equal to the square root of 2gm over r. This is called my escape velocity. It is the velocity I must fire a projectile with in order for it to escape and never come back. Assuming, of course, that there are no other forces acting on it when I, while it's in its ascent. So rockets are going way slower than that. This is like kilometers per second. So rockets are going way, way slower than that when they escape. So how do they escape? They're not at the escape velocity. How does a rocket make it?
Constant thrust.
Yeah, it's got a thrust. There's a force constantly acting on it to get it out, right? So that's fine. This is the requirement of if I just shoot it up and then nothing else is acting. That's it. Obviously, if I have a force that's just constantly moving the thing upward, then that can be escape as well. Okay. Cool. So that's how we do that. It's important to recognize that the whole key to that problem was the escape condition, was recognizing what do I mean when I say escape? I mean that it's somewhere moving around out there, which means that its total energy has to be at least 0, if not greater. That's this and that's next. Okay, that's escape velocity. So the second problem that we can do on this is that of finding out what the energy in a particular orbit might be. So here's again the planet Earth, and here's some orbit. The radius of the Earth is capital R again. The radius of the orbit is little r sub O for orbit.
Are you entering that from the surface?
From the center. I could say this. Define something called h, which is the height above the surface of that orbit, right? Which is, and this is what I'm saying about people losing points, is because they just sort of immediately assume that whatever height they're given for the orbit is from the center, but it's not. And a lot of times, people in exams will try and trick you or trip you up a little bit by giving you the height of the surface, which you need to add to the radius of the planet in order to. But I'm being nice, and so R naught for me, R O orbit, is measured from the center of the Earth. Okay. So, what's the answer? Well, E equals 1/2 mv squared plus or minus G big M little m over squared. Well, what's v squared? Can I figure out v squared?
Why is R not squared in this case?
It's not, because I don't know how to do physics. Thank you. Okay. So, can I find v v squared? The answer is yes, because what else do I know, right? I'm looking for v squared now. So this is, if you want to think about it, this is a comprehensive problem. I want to know what the total energy is in a given orbit, and I'm guaranteeing you that given only the radius, you can calculate what it will be if the orbit is circular. So it's obviously this is the form, but you haven't figured out v yet, and I'm telling you that you can figure out v from the radius of the orbit, which might seem kind of weird, right? But that's the problem. Understanding the system. What forces are acting on it? Only the one, right? Only Newtonian gravity is acting on this guy. Identify a path to solution. How the hell are we supposed to find v? We can do it because what do we know about the motion of the object, right? Here's my satellite, or my orange that's floating in orbit around Earth, whatever you want to call it. Think about it. There's something in orbit around the Earth. What is the net force on that object? Is it zero? What would it mean if it was zero?
Straight line.
Straight line, constant velocity, right? But it's clearly not moving in a straight line at constant velocity. What kind of shape is it moving in? Circular shape. So what do we know about the force? So the force on the thing, the net force, is the centripetal force, which must be equal to little m v squared over r. It must be equal to that, because that's the defining characteristic of the thing moving in a circle. But what is providing centripetal force? Gravity. Right? So this must be equal to this. So there is a centripetal force, must be equal to mv squared over r naught. But it's being provided by Newtonian gravity, so it's equal to g squared. Yeah.
R squared.
Yeah, that actually should be there. Because it's the gravitational force, not the gravitational potential energy. Makes sense. Yeah, done. Because remember, this guy is squared, but this guy is no. So earlier, I was talking about this, but now I'm talking about the force that gravity is exerting on the thing, which is this guy. So this guy. Okay. So, but look what I can do. I can multiply by r naught, and I can divide by 2. What happens if I do that? On the left-hand side, 1/2 m v squared, and that's equal to g over. So look what I found. I found that because it's moving in a circle, that this must be the force on it, but it's provided by Newtonian gravity, and by doing a little manipulation, I found that the kinetic energy in that orbit must be this. So it is determined exclusively by the radius of the orbit and the fact that the radius is, or that the orbit is circular. Awesome. So from that, I can plug this into here, and I get gm little m over 2r naught minus gm little m over r naught, and so the total energy E is equal to minus g big M little m over r naught.
How'd you get the 2 or not?
Here,
Yeah.
because I multiplied by r naught, which gave me over r naught, and I multiplied by 1/2 to get 1/2 m squared.
Oh, okay.
What would the little n be in this case?
The mass of whatever I'm talking about. So be it an orange or a satellite or a house or a rocket ship or an astronaut. Or big M is the mass of the Earth, and r naught is the radius of the orbit. So the energy of the orbit, assuming that it's circular, is exclusively determined by the radius of the orbit. Which means that if I have 2 orbits, and I want to get from one to the other, I can calculate how much energy I need to add or subtract to the system. Right? So here's the Earth. Here's orbit R1. Here's orbit R2. Right? With radii R1 and R2 respectively. The energy of the first orbit, the closer one, E1, is equal to minus G big M little m over R1, or 2R1. The energy of the second orbit is similarly minus G big M little m over 2R2. And so if I start from R1 and I want to get to R2, what do I need? Well, the change in energy, which is equal to E2 minus E1, is equal to minus G big M little m times 1 over R2 minus 1 over R1, which I can write as equal to G big M little m 1 over R1 minus 1 over R2. Okay? And so, if I'm shifting energy, if I'm shifting orbits, I need to either add or subtract a particular amount of energy, and the amount of energy I need to change is given by this. Okay? So that's how much boost I need, or that's how much I need to take out in order to change my orbit. So you'll notice, by the way, that if R1 is larger than R2, then this is smaller than this, and so I get a negative contribution. So if R1 is larger, to get closer to the planet, I need to take energy out. To get farther away, I need to put energy in. So if you had, for example, a very thin atmosphere, right? You imagine that the atmosphere doesn't cut off, it sort of thinly extends out to infinity. Then any object in orbit is slowly plowing into stuff, undergoing inelastic collisions. It's like drag, right? And it's losing energy. So anything in orbit around the Earth is slowly spiraling inward. So in order to stay in orbit, you would have to continuously sort of boost yourself out every once in a while to maintain the same radial distance, otherwise you wouldn't fall in. Yeah.
What happened to the factor of 1/2?
There.
There, the second and third one?
This
E1
one.
equals
Oh, you're right, I'm
E2
sorry.
equals.
My bad. Over 2 as well. I was getting ahead of myself and just concentrating on the fact that it's not as good orbits, but you are correct. There should be a 2 in there. Yet again, I'm not very good at. Okay? Does that make sense? So taking energy away means it spirals in, which is kind of what you imagine in your head, right? If you had an orbit and slowly energy. Yeah.
If this were to like show up on an exam, could you just say that we already know that the energy is GMM over 2R, or would we have to show why we do that?
I mean, you have a formula sheet, right? So you could just make
That's
reference to the
your
fact that it's on the
formula.
formula sheet, or you could derive it if you feel like it. Whether you do that or not, I really encourage you, when I do these like quick derivations, I really encourage you to do them, right? Even if you don't write them down, or even if you don't do them on the exam, at least do them once, so that they sort of have a familiarity, and then it sort of cements it in your mind. Yeah.
So in the last two lines, how come the 1 over R2 and the 1 over R1
I
are
took this minus
split?
sign, and I
Oh, and you made it positive.
Yeah,
Okay.
because I wanted it to be like a positive number times a thing that can be either positive or negative. Okay? Alright, good deal. So, Newtonian gravity. Very cool. But we're done with that. Maybe if you guys are like taking notes or writing stuff down, something that you may want to try is if you imagine that you dropped an apple from 5 kilometers above the surface of the Earth, then how fast will it be going when it hits? You can calculate that using the MGH formula, but it would be wrong because it's not. Let me really quick show you why this is. If I write R12, so if I imagine that I myself am on the surface of this planet, and the planet has mass m and radius r, then the force on me, or on anything, can be written as follows. Okay? Where r is the radius of the Earth and h is the height above that. Right? So the distance from the center of the Earth is the radius of the Earth plus any little bit extra. So, what if h is equal to 100 meters? Big football field up in the air. What is r plus h? meters plus 100 meters. Okay? It is, for all intents and purposes, exactly 6.5 million meters. Right? So the height h has not appreciably changed this distance. So what you can do, for an example, is you can say, all right, well, what if I have f1 over f2 equals minus g big M little m over r plus h1 over minus g big M little m over square r plus h2 squared. Right, this becomes, everything cancels except r plus h2 over r plus h1. This is squared. And I can divide top and bottom by r, and this is equal to 1 plus h2 over r. 1 plus h1 over r squared. And what you find is that this is really, 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 really close to 1 for almost any value of h that you would deal with in an ordinary problem. Anything less than 1,000 or 10,000 meters, it's essentially, this is basically equal to 1, which means the force is essentially independent of the distance above the height, above the Earth's bar, unless that distance happens to be comparable to the radius of the Earth itself. So if you are like if you're a million or if you're a million meters above the surface of the Earth, this is no longer 1 anymore, right? So now we really can't use what's called the flat Earth approximation, or the flat gravity approximation, which is that F equals minus mg. This doesn't work if you are like a distance from the surface of the Earth that is comparable to the radius of the Earth. But as long as you're staying really close, then this is fine. Okay, so that's, by the way, how they're different. And so you might also, one last thing before we call it quits on Newtonian gravity, is what is, if it's the same, what is that force? And you can see that if h is really small in comparison to r, that the force is approximately equal to minus g capital M little m over r squared, where r is the radius of the Earth. And if you calculate this, g big M over r squared, okay? And this is obviously constant. Mass of the Earth is constant, radius of the Earth is approximately constant. And you get that. So, magic trick, right? That's what little g is. We defined little g to be that thing. And this is in units of meters. Okay. So that's just the last thing about Newtonian gravity, but you can see the connection between Newtonian gravity and the flat. It's much easier to use, obviously, than Newtonian gravity. Newtonian gravity is more complicated because the force varies with distance and things like that. So when we can get by just approximating, we do that. Okay. Let's take one more. Do you have the time for me?
10, 12.
All right. So I'm going to try and do this in 20 minutes. But to do that, we're going to have to close our eyes for 10 seconds, decompress, because this part is going to suck. Shot. All right, rotation, angular stuff. Let me restate the correspondence that I mentioned last time. Last time I said x of t corresponds to theta of t. So that means that x dot, which is initially our velocity, corresponds to theta dot. This is usually called omega of t, but I'm going to avoid doing that because I'm going to try and use the symbol omega as little as possible. So I'm going to just call this theta dot whenever I possibly can. And so similar, we have the acceleration, which we used to call x, or which we're calling x double dot, t, right, which would correspond to the angular acceleration, which is theta double dot. Just as a reminder. We're also going to have a correspondence between the dynamical things. So force is going to correspond to torque. And mass is going to correspond to moment of inertia. And momentum, P, is going to correspond to angular momentum. Okay. These, we got these as well. But where this is a very simple thing, these are not so simple, right? Because, as you know, the torque on a particular system is a little bit more complicated than the force on that system. The moment of inertia of an object is related to the mass of the object, but certainly more complicated. And the angular momentum is similarly more complicated. I should point out, though, that in this correspondence, we have definitions that still apply. Newton's law, which used to be F equals ma, in a rotational context, can be shown to correspond to torque is equal to I. I'm sorry, let me write this. That, x double dot. Okay. And similarly, we have the definition that momentum P is equal to mv, or mx dot, which now is going to correspond to the definition L is equal to I times. So I'm not going to, for the rest of this, explain and try and give you physical intuition as to why moments of inertia are what they are, why they're greater or less than that kind of thing, why they depend on the shape, because we don't have time. If you want to know, then I'll be around a little bit afterwards, and again, you can come back tomorrow or go on office hours or something this week, and we can talk about it further. But I can't spend time on giving you physical intuition. I can only really, at this point, give you some definitions and try and help you work through. Right? So, for a solid body, I'm going to imagine, well, the moment of inertia is equal to, well, let's do it this way. Let's do it in a discrete case. So let's say that I have a system that's going to be 5 these things, and they're connected to each other using they're like solid rods or something. So it's basically a bunch of things stuck together so they can't move relative to one another. This is something that we're going to call a solid object. That's what a solid object is. Okay? It is a collection of individual small particles that are not allowed to move relative to one another. They're allowed to move, certainly, but not. I'm going to label them. So this is going to be 1, 2, 3, 4, and 5. I want to know what is the moment of inertia of this collection, of this object. And I can't do that without defining for you the axis about which I'm going to try and rotate it. Okay? Because the moment of inertia of a particular collection or a solid object depends entirely on which axis that you're going to try and rotate the thing to. The moment of inertia of this eraser about this axis, right, if I rotate it like this, is different than the moment of inertia when I rotate it like this, which is different than the moment of inertia when I rotate it like this. Right? So I need to define for you what that axis will be and where it is. So not only in what orientation, but also where physically connected to the body. And so I'm going to say right here. This is the axis, and I'm going to rotate it this way, or this way. I'm going to rotate in the plane of the board. The one definition that you do need is the moment of inertia of an individual object, I. So I, so little I, unfortunately, is equal to the mass of that little piece times the distance from that axis of rotation, which is R1. I'm not going to draw, that'd be a horrible mess, but this is R1, R2, R3, R4, and R5. Okay. And so the distance from that axis, and it should be stated that it's the perpendicular distance to that axis. And what I mean by that is, if I say the axis of rotation is the, that line, that corner right here, like this, connecting this guy to that wall, that's the axis of rotation, then the distance of this point to that axis of rotation is exactly the same as the distance of this point to the axis of rotation, because it's the parallel distance, which means, or the perpendicular distance, which means that I go here and I go in a perfectly perpendicular line to that axis until I hit it, and that distance is what I'm calling r. Okay? So it's important to note, just in the sense that, if this is my axis, I don't try and measure a distance from the eraser to be like this. Right? It's always perpendicular to the axis that I'm trying to measure. Okay? So this is the moment of inertia of an individual object, which can be derived using this law. So, given that, then, how can I find the moment of inertia of the collection? And it's very simple. The moment of inertia I is just simply equal to the sum of those. So if I've got three objects and I define an axis that I'm going to try and rotate them about, then I calculate what R1 is, R2, R3. I know what mass 1, mass 2, mass 3, and the total moment of inertia of the whole system about that axis is this. Simple enough. But with a solid object that is sort of continuous, like a table or something, that really what it is on an individual microscopic level is we're adding up, we imagine that the atoms that make up the object, right, are those are the little balls, and they're connected by atomic bonds, which are the sticks. And so we're just adding all those up, but there's way too many of them to imagine actually doing a sum. So we have to take an approximation which then is continuous. Like if it's continuous, I can replace this with an integral. Integral of the density of the thing times r squared, and I do this over let's do dx first, dr. This should be taken over the entire body of the object. So if it's a one-dimensional object, like a rod like this, right, then it would be dx or dr, whatever you define for it, and I'll do it in a second. If it was an area, like a table, right, where we didn't imagine it didn't really have much of a depth this way, but it does have an expanse like this, then I would have to integrate over the length of the table and the breadth of the table. Right? And if it was a three-dimensional object, like a person, you would need to define an axis and then integrate it over the whole volume of my body. Right? We'll never have to do that. So we'll just worry about the one-dimensional case. The two-dimensional case is a simple extension, but it's more involved calculus-wise, and we're not going to do it. And so I'm going to calculate the moment of inertia of a rod. I'm going to do the problems on this last quiz, because that was kind of so this is where I'm going to take this is where I'm going to take the example problems that we're going to do for this section is off this last quiz that we did. Okay. So the first one, the first problem, the example was calculate the moment of inertia of a rod of length L. So this whole length is L. About a pivot point that is 1/3 of the way down. This is L over here. Calculate the moment of inertia of the rod about that pivot point. Right? So the first thing I'll do is direct integration, which is always possible. You can always do it, although it might be a pain in the butt. So let's see how we do it. The integral is the moment of inertia I is equal to the integral of the density rho, or if you prefer the density lambda. I know that for some people, I'm not sure if that really does it or whatever you uses rho. It doesn't matter. We just mean the density, which is the mass of the thing divided by its extent. So if it's an area, it's rho over its mass divided by the area. If it's a length, it's mass divided by the length, whatever. So in my case, I'm defining rho as mass m. I'm defining rho as mass divided by length. Right? So it's rho. I'll define this coordinate as to be x, right? And x is the distance along the rod I've gone from, I shouldn't draw it like that, from my pivot point. This is my x. And so if I define it that way, then I get rho x squared dx, and it runs from what? What are the bounds of this integral? I need to cover the whole rod, so where do I need to integrate this from? 0 to L? No, because 0 rho starts here and L starts here, and that's not covering the whole rod. So that's it. So that was number one, where we had a decent amount of confusion there. Okay. So the integration bounds are crucial. And you know, especially if you're in my class, 'cause I've done it like 8 times, but if you shift the integration bounds, you drastically change what the moment of inertia is going to be. It's going to be something times m times L squared, but that fraction in front is enormously dependent on what these guys are. And if we do it this way, we do some calculus, this turns out, this turns out to be equal to ml squared over 9. And I encourage you to give that a shot and try it out. Right? But that's what we do. However, I'm going to do a slightly simpler one, and the way I'm going to do it is I'm going to use our friend, which is the parallel axis theorem. Which states that the moment of inertia of a rod is equal to the moment of inertia about the center of mass plus r squared, where I now define, again, this is an overloaded variable now, so r is not a raised here anymore. R is the distance between the pivot point and the center of mass. So in my case, if the center of mass is right here, right, halfway down the rod, this is my r, which happens to equal L over 6. That's the distance. Okay? This is enormously useful because I don't have to do any integrating and integrating. So, what do I get when I do that? This one I will do all the way out. When I apply the parallel axis theorem, then I is apparently I center of mass. Does anyone remember the center of mass moment of inertia of a rod? ML over 12 or something, or ML squared over 12. So ML squared over 12 plus this is M times L over 6 squared. Okay, because this guy, which is 1/3 of the way along, is 1/6 L away from the center. Or L over 2 minus L over 3 equals L over 6. Like that. And so this is equal to ML squared over 12 plus ML squared over 36, which is, yeah, so this is 3 ML squared over 36, which is 4 ML squared 36 together, which is ML squared over 9. Fantastic. This is way easier than that, but you can do either one. If you love calculus and love integrating and love playing with this algebra stuff, do that. Or you can use the parallel axis theorem, which is in general going to be easier and less computationally intensive. Okay. So that is the solution to the first problem on the exam, or on the quiz that we did. I haven't seen the exam. Write that down. Just playing it close to the rest this time. Okay, so the parallel axis theorem or direct integration, either one you can find here. Okay? Alright, simple, easy peasy. So, put that off to the side for a second. The other exceptionally important thing, one of the other exceptionally important things, there are 2 huge bits. The first is rotational kinetic energy, and the second is angular momentum. Okay, so I'm going to do them in that order because rotational kinetic energy is going to play a role in a second. All right. The total kinetic energy. And this is, I'm going to repeat this 3 times because it is wildly important, and it is something that almost nobody got right. Almost nobody. The total kinetic energy of a moving object, a moving extended object, is the kinetic energy of its center of mass, which is to say, you concentrate all of the mass in one spot, which is at the center of mass, and you look at it go like a point particle, which is 1/2 b center mass squared, if you prefer. Total mass b center mass squared plus rotational kinetic energy. And this is the part that almost nobody got right. About the center of mass. That is wildly important. This is plus 1/2 I theta dot squared center of mass. Okay. So that's hugely important. So again, to reiterate, when you calculate the total kinetic energy of something, it's the translational kinetic energy of its center of mass, plus its rotational kinetic energy about the center of mass. Not about some arbitrary point that you've decided, but about the center of mass. You must calculate it about the center of mass. Otherwise, this doesn't work. You can write the total kinetic energy as the sum of the kinetic energy of each individual atom in the solid. And if you do that, it becomes this horrid mess, unless you use this wonderful definition of a thing called center of mass. And if you do that, it all cancels out, and you get two chunks, this and this. But that's only if you calculate this about the center of mass. Okay? This is the velocity of the center of mass, and angular rotational kinetic energy about the center of mass. Okay? Just to be clear on it. So anytime you're calculating 1/2 I omega squared or 1/2 I theta dot squared, you must use I center of mass. Okay? About any other axis doesn't make any sense. About any other points. Okay? And so I will show you the solution of problem 2 on your quiz. I'm not going to do problem 3, but I'm going to do problem 2 for your quiz. Okay? And you'll see how this is extremely important and why almost universally everybody got at least a few points off. Usually more than a few, unfortunately, but all right. The rod is initially sideways. It's at its pivot point, L/3. And then it swings. So now, this. Dot rotating with some angle is changing. So the question is, how fast is this point going when it hits the bottom, when it's vertical? How fast is this point going? We can use the conservation of energy, but we have to be really careful when we do it. Let's see what we get. The initial versus the final, what do we do? Well, there's going to be some kind of gravitational energy, right? But it's an extended object now, so mgh doesn't really make sense. Does anyone have a wild guess as to what we can substitute instead of just h? Hell no. No. So I'll give you a hint. It's not going to be the location of the object, right? It's mgh above some reference level where h is equal to 0. But this is an extended object. It's made of a bunch of objects glued together. So instead of saying h, which would correspond to an individual object, what should we use? H. We should use like an average h, right? Which is like corresponds to like average height above the thing. Does that maybe make sense? But what is the average? What is that called? So instead of that, now let's just mgh center mass. That is the gravitational potential, or the gravitational potential energy. So if this guy knew, because here's my center mass at the end, here's my center mass at the beginning, what is this? So I should probably write this as h equals 0 at the bottom. Would you agree? Because the potential energy at the bottom should be 0. So this is h center mass equals 0. So what is this guy? Or 6. Okay? So we need to look at, when we're talking about gravitational potential energy, we need to look at the location of the center of mass. Another way you could think about it is, the gravitational potential energy is mg h center mass, because it's really this. Right? If you have a bunch of objects glued together, it's the sum of all the potential energies. But G is a constant. We use this, which is a good working definition of where the center mass is. We remember our definition of center mass. It's like the average. Or I could otherwise write big M over. That would be more helpful. Right? So big M is the total mass of the object. Little m is the mass of each individual piece that's glued together to make up that solid object. When I add them all up, I can write it in this way, that this is the height of the center of mass. That's what the definition of center mass is. So that's another way more analytical. Regardless, however I feel like doing it, the initial energy, EI, has no initial kinetic energy, so I'm safe for that, and all I get is big M times G times L over 6, which is the initial height of the center of mass, assuming that ends up. Okay. Good. This part is the complicated bit. Okay. Final energy. Final. Equals. Now we have to do the kinetic energy. So what is the translational kinetic energy of the center of mass? Yeah. So it's going to be, well, we're going to 1/2, okay, and fine. But what is the velocity of the center of mass? Theta dot, not squared, but theta dot times something, right? Times, but what's R? Ah, yes, right? Because the velocity of a particular spot on a solid object, the translational velocity of that spot is equal to the angular velocity of the whole object, which is a constant, times the distance from the pivot point of the point you're talking about. So the translational velocity of the center of mass is theta dot times this distance, L over 6. M L over 6 times theta dot. And all of that is squared. So if that's what you meant by theta dot squared, then yes. Right. That, which is, and I apologize for those of you that are having trouble seeing it, so I'll come on. So E initial mg h center mass, which is equal to mg L over 6, and E final is equal to 1/2 m L over 6 times theta dot squared plus 1/2 times what? I, right? Yeah, right? Not the moment of inertia about the pivot point, which is ml squared over 9, but the moment, or the moment of inertia about the center, which is ml squared over 12. 1/2 m L squared over 12. And I can do some algebra to combine this. This becomes 1/2 big M. I apologize for my erratic use of capital and lowercase m's, but it doesn't matter. I'm asking the problem. But consistent, really capital the whole time. And this is 1/2 m L squared over 36 plus 1/2 m L squared over 12. But remember, 136 plus 112 is 19. That's the initial calculation we did, right? So this is equal to 1/2 m L squared over 9 times theta dot squared, which is equal to m L squared theta dot squared divided by 18. So that's the tricky bit. So you can see how this is really easy to mess up if you use the wrong moment of inertia. Whenever you're calculating the rotational kinetic energy, you must calculate the moment of inertia about the center of mass. But I've gotten to this point, so now what do I get? I get that E initial is equal to E final because energy is conserved as it falls. The only thing acting on it is gravity. The only thing that work on it is gravity. And so that means that mg L over 6 is equal to m L squared theta dot squared over 18, or cancel m, cancel one of my L's. Theta dot squared is equal to 3g over L. Theta dot is equal to the square root of 3g over L. And I am almost done. I have now found the rotational velocity, the angular velocity of the thing. But I didn't want the angular velocity. I wanted the velocity of the bottom.
For energy final, why is there two different terms? What does each term stand for?
They are the rotational and the translational kinetic energies. Right? So you have the kinetic energy, the translational kinetic energy of the center of mass, right? Which is just 1 half mv squared. And then you have the rotational kinetic energy about the center of mass. Okay. So you can imagine a cannonball being fired. It doesn't have the same amount of energy if it's just sort of at rest but floating through the air, or if it's wildly spinning as it's floating through the air. No, it has more the second time, right? So you have to take both the translation of its center into account as well as the rotation about the center. Thus the origin of the two terms. So with this, with that, all these things add together, algebra, whatever, I get theta dot. Last piece, I want the velocity at this point. What is it? Velocity at the bottom. Velocity at the bottom, v is equal to, that's it, right? Because the velocity of any point is equal to the angular velocity times the distance of whatever point you're talking about from the center, from the axis of rotation. So we know theta dot. I care about this point, and it's 2L over 3 away from the axis of rotation. So the final velocity is 2L over 3 times the square root of 3g over L, which could also be written as 2L square root of g over 3L, or lastly, it is like square root of 4/3 GL or something. Any of these is fine. But you have to understand that that last problem was really involved. Right? That wasn't simple. That wasn't something you just write down. That was difficult. Right? Because you must understand that this is the velocity of the center of mass, and this is the moment of inertia about the center of mass. Only then can you solve all this stuff out and get the correct fractions, the correct numbers, find theta dot, and then you need to again recognize the relationship between v and theta dot. All right, so here's the deal. It's getting really late. So I am going to, I'm going to stop here. Okay. There is more to it, right? There is also angular momentum and there's also torque. But what I'm going to do is, those of you who are going to be here tomorrow, I will start with that and then open the floor for torque. My goal for tomorrow, by the way, is to everybody here. My goal for tomorrow, what I want to do is, once I've gone through whatever I have in here, I'm going to open the floor completely to individual questions. So you need to come prepared with questions. And so the way that you do that is you should take the first exam and the second exam, which I believe are both on Alice. Is that right? Right? Look at them both. Download them both. Take them both again. Just sit there and just try each exam. It doesn't matter if you get them right or wrong, but just give it a shot. And so when you come back, right, tomorrow night, after I finish the torque angular momentum part, what you can then do is say, I had trouble with this bit, can you help? Or I had trouble with that bit, can you help? So please, 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 if you're going to be here tomorrow, come prepared with some questions from the previous exam, or from anywhere else.